Hello everyone, welcome back to my channel. Thanks guys for subscribing. Continue subscribing. In today's tutorial I'll talk about SymPy, which is the symbolic computation library that is available freely of charge in Python. Alright, so we'll just try to add on the previous tutorial. If you have not watched it, please go ahead and watch it. So basically what SymPy does is to make sure that it enables you to deal with the symbols in Python, and you can be able to write your expressions and formulas as they are, and then finally you can compute them, or you can substitute for some of the symbols within your expression. So what you're going to do is to first of all import our SymPy, and because I'm going to be using only SymPy, so I'm very free to import everything that is available within SymPy. And so I'm going to simply begin by saying from SymPy import star, that means everything. And then if I run that, then I'll be able to go to the next cell. And as a test, I'm going to first of all import our questions that we are going to do. Our markdown, if I run that, we are going to deal with this expression of the force that exists between two charges, which can be opposite, or between similar charges or opposite charges, and this is the Coulomb's force. So what you're going to do, we have imported our SymPy, and then as far as this question is concerned, we can see that we have charge 1, charge 2, a radius, which is the distance in between these charges, and then k, which is the constant. All right, so we are going to begin by importing writing our symbols or our variables. So we are going to define q1, q2, r, and then k being our symbols that I want to use. And because there are very many, so I'm using symbols. All right, I'm using symbols, and then putting this in quotes. So I have q1, q2, and then r. All right, and then finally I have k. So when I'm done with defining all my symbols I'm going to use within this expression, then I can run that and go to the next cell. So basically what we need is to write our equation. So the expression is just I'm going to call it just fe, and this is going to be equal to k, which is times basically q1, all right, which is times q2, and everything is over r, which is squared. All right, so if I go down here and write fe, this is going to be given by q k, q1, q2, r squared. All right, so okay, so now that we have formulated our expression of the Coulomb's force between two charges, let's go ahead and do the substitution for r, q1 and q2. So in order to do that, we are going to make a use of another expression, and I call this one force. This is equal to so we go back in the fe and we begin our substitution by using the subs command. So subs, so we substitute beginning from k. So I'm going to say k, and then this is substituted with 8.988, and everything exponent 9. All right, and so we further go ahead to substitute for q, which is q1, substituted with 2 microcoulombs. So that's going to be 2 times exponent minus 6, and then finally we have these 2, that is dot subs, going to be for q2, which is substituted with the 3 exponent minus 6. All right, so, and finally we have the last one, which is for the distance r, so substituted with 0.1 5 meters, and then this is going to be stored in a variable called force. So let's print out our variable force. So I'm going to say the force between two charges equals, okay, and I would need that answer to go on a new line, so I have that, and then comma, we print force, okay, and this is going to have units of newtons. All right, so if I print that out, run that, this is going to give us the force between two, this is just 2, okay, the 2 charges is equal to that. Basically, that is how we can substitute in expressions, write expressions and substituting basically in any scientific way. So let's proceed to go and look at other expressions and how we can do that. So I'm going to upload some expressions here, and this is going to be 2 JPEG from this image, and that is going to be a markdown. If I run that, in our part 2 we have these expressions, very many of them, so I'll not be doing all of them, and to simplify them, expand and factor them out. So let's see how we can go about this. Basically, we'll begin with the first one. Okay, so x is already defined as a symbol. No, not here. So we'll begin by defining x being equal to symbol. Since it is 1, so we can use symbol with capital letter. So, and this is equal to just x as a symbol. All right, so if I run that, I will go to the next new cell. So let's begin by calling expre, which is our expression, and this is equal to, if you look at that, so open up the brackets, and this is going to be x squared plus 5 times x, then minus 24. That is one of the expressions, and then the lower one, which is the denominator, is x squared plus 6 times x, okay, and then finally plus 8, and the whole thing here is minus, sorry, it's times, okay, so I'll have to put this in some more bigger brackets. That's the first part, and then the second part we have again, I'll create inside an inner bracket, which is x squared plus 4 times x, then plus 4. All right, and then this is over the denominator, which is equal to x squared, then minus 3 times x. All right, so this is our expression from up here. So let's try to first of all print it out and see what it gives us. All right, if I call expression and I run it, this is what it is going to give us, just the way it is right here. So now the task here is to simplify, expand and factor that those expressions. So let's see how we can do this. So I'm going to call to make a use of the functions and methods within the SymPy. So for simplify, I'm just going to say simplify. So I'm calling back my expression, and then I say simplify. All right, so if I do that and I call simplify, okay, and then run that, and this is going to give us this expression. You can see that it is completely simplified at something that is simple by cancelling some of the terms out. And then if we go ahead to expand and factor, I'm going simply to say expression dot expand, and that gives me this expression. So if we expand, you can see that it has been completely expanded, but we can condense all this and then we go back to this expression we had before. still we are playing with the same expression. We are simplifying it and we are expanding it just the way it is. And then finally, let's look at how we can factor that. Okay, because we are looking at simplify, expand, and factor. So I'm using the same. Remember all these methods or all these functions do not change the original function. It remains there as it is. All right, just the way it is. So if you want to create another expression out of that function you have applied, you need to call it something different. Okay, so let's proceed to the factor part of it. So I'm going to say expr dot factor. All right, so when I do that and I run it, this is going to give me x plus 2 into x plus 8 over x into x plus x plus 4. So this is the same stuff, but just expressed in a different way depending on the method we want to go into. So we have factor here, we have expand here, and we have simplify here. So this is how you can play with expressions before even you apply maybe the substitutions. So if I wanted then to substitute, I would simply say expression dot subs. All right, and then I'm substituting for only x with maybe 2. Okay, so that means this gives me the answer as 10 over 3 by substituting just x plus 2, that which x is now 2, that becomes 4, and then over 2 into 6, so that becomes something like 10 over 3. All right, so when you do that, that becomes simple for all the expressions. Let's try to look at these other ones which have reduced the rational expression to the lowest terms, and in this one I'm going only to deal with one, the first one, and this is going to be our expression. I will call it expression 2, which is just x squared. Okay, so this is x power 2, that is plus 6x plus 6 times x, then minus 9, and no, it's plus 9 over x squared minus 9. This is plus 9. Okay, then everything over x squared minus 9. I think someone could see somewhere identity down there, and then when we do that and we call it x2 and run it, this is what we have. So to simplify that, just I'm going to say in the same way, expr2 dot simplify. All right, and then this becomes x plus 3 over x minus 3. Okay, so in order to expand that, I'll simply say expand in the same way, and then if I run that, that's what we come up with. Okay, and then when it comes to factoring, we have just expr2 dot factor, and then this becomes just x plus 3 over x minus 3, and in this case it gives us that. Please, you can proceed and go ahead and work out this. Okay, so this is basically how we can look at such factors. So let's jump to another part, which is the part 3. So this is going to be so if I load that, we have again factoring, greatest common factor of each of these expressions, but I'm not doing everything. I'm going to simply do 2x, this expression number 3, and we see how it goes. X as usual is already defined, but if it was the case of, oh okay, we can do question 2, which involves a, b, and so on. So again, I'm going to begin by defining my symbols. A, b equals because they are more than, it's more than one, so I'm going to use symbols, okay, not just symbol with capital. And then I have a and b. So with this, I'm going to say x as my expression, which is equal to a cubed, then this is, sorry, a power 3, then times this is b power 8, and then minus 7, this is times a power 10, then times b power 4, then this is plus 2 times a power 5, then times b power 2, right? And this is our expression. So if I just go down there and call it, this is what we have: minus 7 power 10 b4 plus 2a power 5b squared plus a cubed b8. So what I'm going to do is just to say x and then factor, ex and factor, and then let's see what this gives us. This simply pulls out minus a cubed b cubed, which is the common factor you can ever get out of that expression, and then the rest goes or remains inside. And if I were to just expand, let's see what it would give us. Just expand. I don't think it will go any much further than that, since it does not involve. But if I were to work out question 3, which is I can call it expression 2, which is just 2 times x, then times the brackets where inside we have x squared, then plus 1, right, and everything is raised to power 3. Then this is minus 16 times brackets where we have x power 2, then plus 1. You can say a common factor of bracket, and then this is raised to power 5. Okay, so I call that x2. If I call it again, you can see what we have, which is exactly what we have here. All right, so now let's see how we can factor that out. ex2 dot factor. If I call that and print out, we can see this is the factor in its simplified way. And then if I say, let's just simplify that. If to simplify that, again, I'm using the same functions. Simplify, I call that, this is what we have. Okay, and when it comes to expanding, so this will be dot expand, expand, and let's see what you have. Alright, so when you expand it, this is what you get. So this is how you can play with all the expressions, how you can write expressions in Python using SymPy symbolic library, and how you can expand, how you can simplify, and how you can factor them out. Okay, so let's proceed with another part. Yeah, so just a reminder from what we talked above here, when it comes to substituting, if you have if you're substituting for the symbols, you could do that at once. For example, in this example here, like we did for the case of this force, just as a reminder, we could do that in one single move, instead of just using the dot subs and sums. If I just recall that again, and we say that would give us that answer. Just as a reminder, again, we would say force equals, we go back to our FE which we had previously, and then now instead of just using the sub dot sub dot sub, then we could have as that, and we have a list of tuples of those substitution and their values, of the symbols and their substitution. So I have a list, but inside I need to have tuple. If you haven't looked at my videos about tuples, lists, and that, please go ahead in Python videos. They are very interesting and to look at. So in this case, we would look at the first tuple, which is which is of k and its substitution, and that's what we have. Okay, and then we continue to look at comma, the next one, which is for the q1, and then that's what we would have next here, and then a comma, and then we have another tuple of containing q2 and then its substitution, and that's what we have. And likewise we have a tuple of the radius, so that's what we would have at last. And then if you just print out the force now, just like that, if you run it, you still get the same answer shortened to the same value. Alright, so this is how you could just substitute everything at once. Alright, so let's look at another part, how we can convert strings to expressions. Alright, so the SymPy has the ability to do that for us. If you have a string that is in terms of an expression, you can do that. Let's say we have a string which is string equals string is always put in quotes. If you haven't watched my video on strings, again, please do that. Let's say we have x which cubed, all right, then plus 2 times x squared, okay, and then finally minus 4. Okay, so with just like this means that this is a string. So if we go further to check the type of this variable string, okay, this has to return str, that means string. Okay, so now how do we convert a string if to an expression? As we can see, this is x cubed plus 2x squared minus 4, a string form. But then if we want to convert it to an expression, so we can say expression, and this is equal to, we can use a function that is called SymPy. So this is SymPy. Okay, please note it is SymPy. Okay, of what? Of the string. And when we do that and we call back our expression, let's see what we have. We have x cubed plus 2x squared as our expression. And so if you want to go ahead now and substitute for x, so then I can simply do the same as we have been previously doing as subs. Okay, that is for x and 1, and that will give us minus 1 if we substitute. Okay, so that's how we can convert expression how we can convert strings to expression. Let's try to look at a more complicated way of writing expression. All right, more complicated way of expressions. Okay, let's assume you want to write a more complicated equation. How can you do that? Let's just look at an example. We already have I think x, y, z, I think in our notebook imported as a function. Let's see, we have q1. Okay, q1 and then the x. Okay, let me just assume I have a complicated expression that I want to write, and this is I have in brackets, okay, I have q1, which you already have as our symbol, then plus q2, all right, and then this is raised to power maybe 1 over 5. So how to write that? You can use the fifth root, or but you can as well use the function rational 1, and then because it is 1 over 5, so you put 1 over that. All right, and then this is going to be equal to, minus, let's have another, let's say we have a constant k that is raised to power a fourth. This is going to be rational k of 1 and 4, and then this is plus maybe 4, and let's say everything is going to be over some other bigger expression, and this is going to be maybe the 2/5 of something. Okay, so I'm going to say this is let's say we have x minus let's say q1. Okay, and this is power maybe 3, and the whole thing is raised to power, we use rational, and this is 2/5. Okay, so if we print that out, we say comp, let's call it and see what we have. Comply is not defined, so let's see. Okay, this is capital C. I am supposed to have capital C here. If I call that, this is what we have. All right, so you can see how big this is. It's very big expression, but you can write it in any of your own way. All right, so let's look at everything to do with the trigonometry. Okay, we have looked at expressions. Now let's look at trigonometry and some of the gymnastics of trigonometry, how we can simplify trigonometry, and all the sorts of techniques we can learn about trigonometry. So basically, first of all, what we need to note is SymPy names trigonometry as Python does. Okay, as Python does. Okay, so for example, if you want to look at the arcsine or arccos of a certain angle or of a certain number, then it does it in the same way as a cos, meaning that is the arcsine or the arccos. Okay, so let's try to look at arccos of a certain value, okay, of say, let's say 1. When we do that, that will give us 1. Okay, and if we say of 0, let's see what we have. It will be pi over 2. Let's look at a sine, which is the arcsine of 1. Okay, and let's see what we have. That will give us pi over 2, since it is the sine inverse of 1 that is giving us sine inverse of 1 that gives us 90. Okay, all right. The same thing if we were to say a sine of pi over 2. Let's see what we have. It would just give us as 1. So the same as tan of 45, which is pi over 4. Let's see what it would give us. It would give us 1. All right, so that means SymPy works basically in the same way as we would work with trigonometry in Python. So having looked at that, let's try to look at the how we can simplify expressions how we can simplify in under Python, or how we can simplify trigonometry expressions in Python. In order to do this, we use a function that is called Trig simp, which means simplifying. All right, so let's see how it works out. Let me say I have an expression which is equal to let's say sine of x. Okay, and then the whole thing is raised to power let's say 2, and then this is plus cosine of x. Okay, these x's and whatever symbols here need to first of all be declared as symbols. All right, so if I have this, and for anyone who has done trigonometry, can tell that this is just equal to 1, right? Because we know an identity of sine squared theta plus cosine squared theta just equal to 1. So if we say trig simp, okay, trig simp, which is like simplified trigonometry of this expression, let's see what we have. It simply turns out to be 1 because we know that is just our first identity in trigonometry. And let's look at just some other expression. Let me just assume this same expression now we modify it to say minus 3 times sine of x, and then this is equal to, I mean, that's raised to power 2, okay, which you can add, and then plus cos of 2 maybe times x, all right, and then minus 2 times sine of say x, okay. Let's see what this would give us. I just copy that and paste it here, simplify that expression. This would give us minus 5 sine squared x minus 2 sine x plus 2. Note that you can see that cosine might find that this is just replaced with 1, alright, because this is an identity 1, and then we have this 3 sine squared x squared, and then this cos 2x, which is can also be expanded and converted only in terms of sine. That gives us some simplified expression. So this function is very stronger when it comes to simplifying expressions in trigonometry. So we can do the same thing with hyperbolic function. We can expand that and simplify, and it's much like simplify and so on, okay. So let's try to look at the expand function, okay. So basically what we looked at here is I will make this one a small heading, the trig simp function, okay, and this is what we have been using, trig simp function. And then now let's look at the expand, so which is the expand trig, okay, expand trig as another function. We are going to see how helpful it is in terms of expanding trigonometric functions. So to do this, we know that we can have expressions of trigonometry, for example, like sine of q1, you have q1 then plus q2. These are like angles, compound angles, and then you want to expand that. We can make a use of expand trig function to do that for us, and let's see how stronger this is going to be. So I'm just going to use my my expand trig, okay, and of what, of just ex, which is equal to sine q1 plus q2, and let's see what we have. This will give us equation expression that is sine of q1 cosine of q2 plus sine of q2 cosine of q1, which is the usual known identity once you expand the sine of two angles, let's say a plus b. Okay, so this is what we have, and that much can apply to anything we know in trigonometry. Let's say if we have again expand trig of, let's say, a usual angle of tan, let's say 2 of x, okay, that will give you the familiar identity of 2 tan over 1 minus tan squared. So these are the some of the functions you can make a use of in terms of trigonometry. And just like when you apply the same, like this upper function like trig simp. If you simplify this, you straight away go to tan of 2x, and then the same applies to that. So it's like it will be a reverse. Let's look at exponentials and logarithms. So we look at exponentials and logarithms and see how we can deal with that in general. Alright, so under exponentials and logarithms, basically when we talk about exponentials and logarithms, we go deep into the e and the logs of any base, but in this case, in this tutorial, we'll try to keep it short and then just look at the laws of logarithms and how we can manipulate logarithms. Alright, so if I write just log of x, in this I'm trying to mean natural log of that symbol, which is x, okay, which is equivalent to the natural log or L of x. Okay, so we will see also how we can specify any other base, but before we do that, let's try to first of all look at the laws that support logarithms. In order to be able to successful with the laws, so I'm going to first of all state two conditions that will hold for the laws of logarithms. Let's use the common a's and b's. I'm going to begin with symbols of a and b. These are my symbols, and the condition for this is that there must be positive. All right, so positive equals true. That's one of them. So when it comes to the powers, n equals a symbol, which is a power. Okay, symbols, I can use symbols, it works either way. And then n, this symbol, which is n, is supposed to be real. Alright, so real equals true. So when we have this turned on in our workspace, let's try to look at the laws of logarithms from just the algebraical perspective. So to be able to succeed, we know that we have log of a times b, that is expanded as log of a plus log of b, and if we have log of a over b, that is expanded to minus. All right, so we have a function that is called expand log. Okay, I'm going to keep this one as my simple heading. This function expand log helps me to expand all the logs. So I'm going to say expand log, okay, of what? Of log of a times b. When I do that and I run, this is going to give me log of a plus b. Let's try to look at expand log of a over b. Okay, divide by b. Let's see what this gives us. To give us log of a minus log of b. Alright, so now that we have looked at the multiplication, the subtraction or the division, let's look at how we can expand log of, let's say, a power 5. What does this give us? There is log here, okay, and that's 5. So if we do that, we'll have 5 log of a. So basically this completes all what we would need to know in manipulating logs in terms of the powers, the laws of addition and laws of subtraction. And so basically that's what we have in logarithms. You can manipulate that as much as you want, and in terms of the powers, you can deal with the powers and as much as you can. Let's try to see if you had you wanted to move in the backward direction, then you would make a use of the log combine command, which is the log combine function. Let's say you have a log of a plus log of b, and this is equal to some expression which is z. Okay, and say if I say log combine, okay, of z, and then let's see what we have. We'll simply have log of a b. So it combines following the law of addition of logarithms, and we come up with one combined log, simplified log of a b. So that's basically what we have. Now let's try to look at calculus. Okay, calculus is a big interesting topic. Let's try to look at calculus as a big topic, and we will try to address some of the main important issues under this part calculus. Okay, when talk about calculus, basically we are looking at mainly differentiation, integration, and in differentiation we are looking at how you can find the derivatives of some functions, and integration we are looking at how you can find the integrals of some functions. All right, so basically how we do that, we will again stick on our already defined symbols, that is the x, the a's, and so on. And to do that, first of all, I'm going to switch on one function that will help me to print my stuff well, which is the init printing. Okay, and I'll keep that one. I'll say use the Unicode, which is true, and switch on that so that I can have my expressions well printed out. So let's see how we can deal with, first of all, the derivatives. Okay, let's see how we can handle the derivatives, and we will then continue to the integration. So under the derivatives, we are looking at the functions obtained after differentiating some functions. Okay, so how do we differentiate basically functions? So we already know that x is already imported in the system. So how to do that? We will use the diff function to differentiate. Okay, so how to go about that? Let's say we have an expression that is equivalent to x power 3. All right, so if I want to differentiate that expression, I'll simply say diff, okay, of what function. I have my expression here, and the variable or the symbol used is x. So if I run that, this is going to give me 3x squared. You can see that it is well and clearly printed out as the derivative of x cubed. When you differentiate it, the power comes in front and we subtract off. So let's test with the cosine and the sine. If we have sine, okay, of x, and it's in terms of x, if I differentiate that, this will give me straight away cosine. If I test with cosine, okay, and I guess you can guess the answer before it comes out, it is in terms of x. That will give us our minus sine x. Now let's try to advance to look at some complicated stuff. Let's say you have a tan of maybe 2 times x. All right, and then this is minus maybe 1. Okay, if I do that and differentiate, this will give us 2 tan squared of 2x minus 1, then plus 2. Okay, so finally, to check more, we can check on differentiate of log of x. That means natural log of x, and the symbol used here is x, so that will give us 1 over x as usual. So this is how we can apply the diff command or diff function that finds the derivative of a certain function, as we have seen. So anything to do with differentiation, you can apply that one. And basically here, this is where you first of all find the first derivative. So I can also add that one up as a first derivative. Okay, derivative. Let's see how, if you wanted to find second, third, and so on. I'll just bring back my expression right here, the expression x power 3, and then let's say we wanted to find expression, the derivative of maybe of that expression, maybe 4 times or 3 times. 3 times, then I have x. All right, 3 times. So if we go by 3 times, the first time gives us 3 in front. The second time we're minus 1. The second time 2 in front, that comes to 6x. And then the third time the x in front, and then we subtract off 1. So our expected answer is just 6. Okay, so this is how you can go about that. Or just you can replace this same situation with just the number of times you want to differentiate that function, and just one derivative. Let's say just x. How many times you want to differentiate that? It's 3. Then if you run that, that will give you 6. If you wanted maybe to differentiate 2 times, then I would say I have x, then 2 times, and then run that. That will give me 6x. So basically this gives us the number of times, how much you want to differentiate the function, and that lets us complete the whole thing of the finding the derivatives or differentiation. So differentiating many times. Okay, so that's what we are looking at just right here. And this, I think, gives us a complete understanding of how we can differentiate a function many times or in the first time. Okay, so let's look at finding the partial derivative. Partial derivative of a function. Partial derivatives. So to do that, we are going to make a use of all of us know that we can differentiate partially a function. Let's say we have an expression, again as usual, that is equivalent to exponent of x times y. Okay, times y, maybe times z. I'm not sure if I defined z already as my symbol, but I can repeat here, xy z being equal to symbols, and that is given by x, y, and then z. Okay, to be safe. So when we have that, let's see how we can partially differentiate that. Okay, so we can still use our diff command, mention what we want to explain, which expression, and then we want to differentiate with respect to x, y 2 times, and then z many times. Okay, so maybe y once and z once. Let's see what this gives us. Okay, this gives us this good expression, as we say. Okay, so let's say we wanted to differentiate with respect to z many times, maybe 3 times. Let's see what we would get. We would get something like that, and this would be our final derivative when you differentiate x once, y once, z 3 times. Okay, so this is basically how you can deal again with differentiating partially of the derivative. If I wanted only with x, then that's what I would go ahead and do. because it's up, what is up here is x, y, z. If you differentiate with respect to x, this exponential, this function x, y, z comes down. After differentiating, what remains, since it is a product, it's y, z, and then we have exactly multiplied by the exponential of x, y, z. Okay, so if it was just with respect to y, what would be down is just xz, and if it was with respect to z, what would have down would be just xy, because xy would survive since it was a product. Let's say if it was some kind of addition. Let's say xp 1 equals exponential of, say, x squared, then plus y squared, then plus z squared, and then we need to differentiate this partially, so that will be the diff of xp1. We need to differentiate x, y, and then the z. So if I run that, that will give us 8 x, y, z, e of that, and so on. So another way of providing a derivative of a partial function is to use the actual derivative class. So let's say answer equals, this is derivative class that gives an evaluated derivative. So we are going to differentiate partially exp1, but we need to specify with respect to what. So this is going to be with respect to y and then z. So if I just call again that as my answer, this is going to give me d cubed dz dy dx of that same expression. Let's see if we are trying to do the same operation but with just respect to x and y. So this would give us dy dx 2 times, and then if we are to just do that with only y and z, we would have dz dy just like that, unevaluated. But if you wanted to just do the same stuff here, then you would just say which is evaluated, then you would just use the diff function, then which gives us the 4yz x squared plus y squared plus z. So this gives an evaluated answer, and the other one gives an unevaluated answer, which remains as the 2 dz dy. Okay, just like that. So this is all to do with differentiating many times as you want, finding the derivatives of any function many times as you want to have seen that, and you have seen how you can partially differentiate a function that is in terms of any other variables. Okay, so let's try now to move ahead to the sweetest part, which is the integrals. Okay, we need to know how can we find integrals. Okay, how can we integrate, or how can we write integrals in SymPy? So just integrals, we have to understand 2 things. One of them is the integral, and one is the integrate. Integrate is the function or the operation, and integral is the expression. Okay, so let's try to look at the difference between integral and integrate. Okay, so when I come down here and I write integral with capital I, so this is integral of x cubed. All right, and the function here basically is x. So if I run that, this is what I'll get. Okay, integral of x cubed dx. Okay, if I wanted to have that with limits, I would write it in this way, that of x, but then I need to specify the upper limit and the lower limit. Let's say we have a and then we have b, and this is going to give us oh no so no, this is going to be x, a, b, and if we do that, this is going to be we are integrating with respect to x from a to b. Let's say we wanted to integrate that function from maybe minus infinity to positive infinity. We use this the oo to mean minus infinity, and the plus oo to mean minus positive infinity. And if I do that, this is what we get. So basically this explains us what an integral is. An integral is this expression. Let's say we wanted to integrate, just perform the integration, itself, and then we need to use the integration command, which is the integrate. Okay, so to do that, I'm going to use exactly the same examples up here, and we are going to say integrate with a small I, integrate, okay, x cubed in terms of x, and that will give us x power 4 over 4. But if I wanted to have limits on this, then I'll have that this is like we have already seen, we need to include the symbol inside, and then from 1 maybe to 4. Okay, and so this is going to be evaluated at that point at x equals 1 and x equals 4. Okay, as we have already seen, 1 is the lower limit and 4 is the upper limit, and that's what we have. So basically this is integration. Let's try to look at integrate. All right, integrate sine basically of 2x, and then we have our symbol is x, and then pi over 4 to pi over 2. All right, so let's see what answer would come up with here. It's just a half. So as well, I can first print out that to display the integral, which is integral of just this, okay, as it is. Let me paste it here. Let's say display, okay, display that, and we have right here the integral of from pi over 4 to pi over 2 of sine 2x. That gives us a half. Okay, so basically this is how sweet this is. So we'll say display another function. Let's say display integral of what do we need? Let's say tan of 2x, or of just x. Okay, and then minus say log of x. Okay, this is kind of complicated, but let's just see what it will give us. And this is x, and then we need from minus pi to just pi. So when we display that, let's see what we have. We have something like this, minus log of x plus tan of that. Okay, so one more expression we can see is, let's say we display, or you can use the print function, the integral of exponent minus x. Okay, and then this is from 0 to infinity. So I have my x 0, and then the positive infinity, which is the oo. Let's try to see this. If I Oh, display has an issue here. This display. Okay, if I run that again, this is what we have. Okay, so this is what we have basically from 0 to that, and then let's try to see if we can integrate that. Integrate that integral. So I'm grabbing this, what is inside here with the limits, and then paste that just right here. So when we do that, oh, I have, I think, extra bracket here. Yes, so that will give us just 1. So I think this is enough on integration. Do perform as many as you want. And now one more part is to is when you have indefinite integrals that has multiple limits in form of multiple limits, and you want to perform multiple integrals. So let's look at that as one more last part, multiple integrals. Okay, so how to approach that? Let's just create a heading here, and we'll look at how we can perform multiple integrals. So let's have a case where you have maybe you have a function that is partially in x and partially in y, and we are integrating both with respect to x and with respect to y. How can we integrate that? First of all, let's try to write that integral and see how it is. We have exp of, let's say we have minus x squared. Okay, squared, then this is times y squared as well, or cubed. All right, and this is from minus some limits. So we have x, which is ranging from minus infinity to positive infinity, and as well we have y, which is ranging from its limits. I'm just using generally minus infinities as general limits, but you can have your other limits as well. So 0, 0. Let's try to display this and see how it would look like. It would look like this, integrating minus infinity to positive infinity of this and that and the x dy. Okay, so the outer integral is for the dy, and then we have the inner integral is for the dx, and that is due to the arrangement we have here. So if you wanted to just change something, you wanted to have like x outer, then I would just rearrange these inputs, and then we have it in this form as you can see. But another part, so another part is about how do we evaluate limits. So limits can be evaluated based on some function here in SymPy, which is the limit function, and we are going just to look at some of a few expression, and in this case we are going to have we can say limit of a certain function, which is f of x. Okay, and then we have the symbol is x, and then the number we need this function to tend to, let's say, is 0. Okay, so then we can try to manipulate that function. This is how or we can just generally call it x naught. So this is how we are going to be writing our functions. So let's try out one example. Let's say limit of sine of 2 times x. Okay, and this is divided by x. Okay, but we need to know this is divided by x. Okay, so let's have x as a symbol, and then it's when in the limit when x is towards 0. we know that for small angles, sine of a small angle tends to that very angle. So that means sine of 2x will tend to exactly 2x. And what to come to x is just x. So when we do that, we have just 2. All right, so this is basically what we have in that case, as just 2. So this limit function evaluates this expression and returns the answer to us as just 2. That's how you can deal with the functions. So let's try to look at another part, which is the series expansion. Okay, how can we expand series using the SymPy symbolic library? So series can be of any form. You can have a trigonometric functions that function that you can expand, or you can just have a mere function of maybe x and you want to expand it. Alright, so under series expansion, we are going to make a use of the dot series function to expand whatever we need. Okay, so it's just dot series, and then we are going, let's have an example of let's say exponential of a certain function. Let's say we have y, or I can say expression, just to keep using expression, is equal to exponential of just x. Okay, all right, so we have now our expression and that is equal to exponential of x. So let's see how we can expand this. So SymPy has a default series of the highest power by default as 6. Okay, you can specify the order of your expansion, or you can just leave it open and then by default it will be to the power 6. Let's see how we can do that. We can use expression dot series. Okay, so I'm just going to specify the symbol and then just run. When I do that, it stops at the order of 6. Okay, but now let's see if I wanted maybe to exceed that order. So in that, let's say we need up to maybe order of 7. So we can say expression dot series, the function, I mean the symbol x, the x naught as the initial order, and then that is maybe 0 up to maybe 9. So if I run that, this will give me from 1 to up to the order of 9. Okay, so the same expression can be expanded maybe to the order of say 3. So I can just grab this and change it to the order of 3. So that way you expand it up to the order of 3 as the highest. Okay, so that is how you can play with the expansion. Let's look at one more expression. Let's say xp equals sine of x. How do we expand trigonometric functions? The same way. So I'll just say expression series, and then I need to mention the variable is x, and then I want to begin from 0 maybe to the order of 5. Okay, so if I run that, that will give me x minus x cubed over 6 up to the order of 5. If I want to proceed and go up to 15, let's see what we have. We have such, you can see, of the order of 15. Right, so basically this is how we can expand. The same way applies to if you had, for example, tan of x and it's what you want to expand. It will be tan x dot series, and then this is in terms of x, and then from maybe 0 to the order of 7. If you do that, that's what you have. And thank you so much guys for watching. Kindly subscribe and share my videos. to share the knowledge with other people. This may seem to be a little bit easy or simpler to some people, but it might be helpful, so helpful to some people, especially those dealing with engineering. Okay, thank you so much.